Hello everyone. Copper isotopes have commonly been applied to characterize the formation of low to moderate temperature hydrothermal mineralizing systems, but only recently have they been applied to study high temperature magmatic sulfide systems. Now, their application to these systems is limited by the ambiguity in how magmatic mineralizing processes such as contamination and sulfide segregation and R factor fractionate copper isotopes. So this study addresses this deficiency by utilizing our current understanding of the processes that generated and modified the copper and PGE sulfide mineralization in the eastern Gabbro of the Coldwell complex to better constrain the effects that these processes have on copper isotopes. The study area is the Coldwell complex in Ontario, Canada. This alkaline complex is located along the northeast shore of Lake Superior and was emplaced into the North American mid-continent rift roughly 1.1 billion years ago. Now, all of the samples are from the eastern Gabbro, which is a composite Pluton composed of various mafic and ultramafic rocks. And the sampling focused on the Marathon, FortAms, and Area 41 areas, as the rocks in these areas are variably mineralized with copper and palladium. Most of the previous work done on the mineralization in the eastern Gabbro has focused on the Marathon copper palladium deposit. Mineralization here and elsewhere in the eastern Gabbro is largely restricted to the Tuduc Lake Gabbro, which is a coarse-grained to pegmatitic gabbro that exhibits a subophytic texture. Mineralization occurs in three dipping lenses termed the footwall zone, the main zone, and the W horizon. Now, each of these zones is characterized by different copper-palladium ratios, with the footwall zone having the highest ratios and the W horizon having the lowest ratios. Now, each of these zones is also mineralogically distinct, with the footwall and main zones principally composed of pyrite and chalcopyrite, and the W horizon being composed mainly of chalcopyrite and bornite. Here we have two box whisker diagrams illustrating the overall variation in copper and sulfur isotopes throughout the mineralized zones in the eastern Gabbro. Now, the overall variation in copper isotopes spans over 2 per mil, which is similar to what has been reported in other NiCuPGE systems. Now, in the Marathon deposit, there's a clear difference in the copper isotope composition of chalcopyrite hosted in the various zones, with the footwall zone chalcopyrite being isotopically lightest and W horizon chalcopyrite being isotopically heaviest and most similar to mantle compositions. Now, this increase in copper isotopes is joined by a simultaneous increase in sulfur 33 as well as bulk copper nickel ratios and a decrease in copper palladium and sulfur selenium ratios. Now, given that these geochemical parameters are known to have been controlled, at least in part, by variations in contamination and R factor in the Marathon deposit, these processes also likely fractionated copper isotopes. Now, chalcopyrite in the northern deposits have copper isotope compositions similar to the mantle, W horizon, and main zone, even though they are characterized by copper palladium ratios that are notably higher than those that characterize the Marathon deposit. Now, all of this suggests that the processes that affected the copper isotope composition of chalcopyrite in these zones is different than those that fractionated copper isotopes in the Marathon deposit. We can compare the variation in copper isotopes to sulfur selenium and copper palladium ratios as a means of characterizing the roles of sulfide segregation, contamination, and R factor in fractionating copper isotopes. Now, these processes will yield different trends on these diagrams, resulting from differences in the sulfide liquid silicate mill partition coefficients and fractionation factor, and the distinct elemental and isotopic compositions of mantle and sedimentary rocks. So, given the generalized parameters listed above, sulfide segregation will generate higher than mantle copper palladium and mantle-like sulfur selenium and copper isotope compositions. Contamination by sedimentary rocks will generate higher than mantle sulfur selenium and negative copper isotope compositions, and high R factors will generate lower than mantle copper palladium and sulfur selenium and mantle-like copper isotope compositions. When comparing the copper isotope composition of chalcopyrite throughout the eastern Gabbro to the average sulfur selenium value of sulfides in a given sample, there is an overall negative correlation. However, when the copper isotope composition of chalcopyrite is compared to the bulk copper palladium ratio of their host rocks, then two distinct trends are evident for the Marathon deposit and the northern deposits. For Marathon, there is a negative correlation between copper palladium and copper isotopes, whereas for the northern deposits, there is generally no correlation. We can model the variations in these elemental and isotopic ratios as a function of contamination using an isotopic mixing model in which one end member has mantle compositions and the other end member is sedimentary rock. Now we can accurately reproduce the observed covariations in copper isotopes and sulfur-selenium ratios in the footwall zone, but not the covariations in the other mineralized zones. So clearly, contamination is not the only process controlling the copper isotope composition of sulfides. Now we can also model the variations in these parameters as a function of variable R factors using an open system R factor model in which contaminated sulfides equilibrate with melts with a mantle composition. Now in doing so, we can generally model the range of sulfur, selenium, and copper isotopes observed throughout the Marathon deposit. This R factor model is also able to generate the covariations between copper isotopes and copper palladium ratios observed in the Marathon deposit, supporting the idea that R factor plays a significant role in generating the variations in copper isotopes in this system. Now, neither of these models is able to reproduce the range of copper palladium and copper isotopes observed in the northern deposits. Higher than mantle copper palladium ratios are, however, indicative of sulfide segregation at depth. Now we can model the variations in copper palladium and copper isotopes using a simple Rayleigh fractional crystallization model, which is able to reproduce the range of copper palladium and copper isotopes observed in the northern deposits, demonstrating that copper isotopes do not fractionate as a result of sulfide segregation. One of the problems with these models is that they do not account for the higher than mantle copper isotope composition in some of the W horizon samples. Now the higher than mantle values likely indicate that the copper isotope composition of the silicate melt with which the sulfide liquid interacted was heavier than typical mantle values. Now this can be simulated using the R factor models from earlier by using initial copper isotope compositions of the silicate melt that are variably heavier than typical mantle values. Now Good and Lightfoot suggested that the mantle source to the eastern Gabbro was variably metasomatized based in part on the enrichment and spread in light rare earth elements in Unit 3 of the metabasalts. Now since metasomatized mantle can have copper isotope compositions that differ from typical mantle values, the heavy copper isotope compositions in the W horizon may be the result of the sulfide liquid interacting with a metasomatized silicate melt. So putting this all together, we have developed a multi-stage model to characterize the genesis of the Marathon deposit. Now consider a conduit-type system with a pool of contaminated sulfide liquid at depth which formed by the addition of sulfur and copper from the surrounding Archean sedimentary rock. As pulses of uncontaminated mantle melts pass through the conduit and interact with the sulfide pool, the contaminated signature of the sulfides is progressively diluted towards mantle values. Now, entrainment and emplacement of sulfides at this stage generates the highly contaminated footwall zone and the less contaminated main zone. Now, interaction with significantly greater volumes of uncontaminated and variably metasomatized silicate melt completely dilutes the contaminant signature, causing the copper isotope composition of sulfides to equate to or exceed mantle values. Now, entrainment and emplacement of these sulfides generates the PGE-rich W horizon. So there are a few key points that I want everyone to take away from this presentation. First, R factor is less than around 10,000, and contamination by sedimentary rocks can exhibit a significant control on the copper isotope composition of sulfides. Sulfide segregation exhibits no measurable control on the copper isotope composition of sulfides at reasonable degrees of fractionation. Metasomatism is recorded by the copper isotope composition of sulfides, and this process may be important for the formation of PGE-rich sulfide deposits. And lastly, copper isotopes are valuable tools for the characterization of high-temperature sulfide systems and identifying PGE-rich sulfide deposits. Thank you everyone for listening.